Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to talk about some basic properties of tensor products of vector spaces, which are absolutely vital to any further study of this notion. And to end this video, I will also talk about an application of these basic properties to a notion of complexification, which is also very, very important. Okay, so the first type of properties I want to have a look at, I've called product type properties. Okay, so why is it that we use the word product when we talked about this construction tensor product? Well, there are certain properties that it has which is very reminiscent of products in algebra. Okay, so let's see what they are. So here we're going to fix the field we're going to work over. That's this F here, and all these Roman symbols, V, V prime, W, W prime, and X, they'll just denote vector spaces over F. Okay, so in what sense do we have product type properties? Well, one of the things that you know is that when you multiply, you have a unit. Okay, so what does the unit correspond to in this tensor product? Okay, so the unit turns out to correspond to, firstly, the very natural vector space of F, just F itself. Okay, so if you do F, tensor over F with a vector space, it's naturally isomorphic to the vector space itself, V. And also, it doesn't matter whether you tensor on the left by this F or on the right by this F, it's still isomorphic to V. And what's the isomorphism? Okay, so to give you this map, I just have to tell you what it does on generators, a spanning set. So F alpha tensor V, these elementary tensors, where do they go to? Well, alpha is a scalar, so you can scalar multiply this V by this alpha to give you alpha V. Okay, so that gives you a map from here to here. You can check by using the fact that this is a bilinear map from F cross V to V. This is this function of alpha and V is bilinear in alpha and V, and so you do get a linear map like that, and in fact it's an isomorphism, as I will prove later. Okay, so that's the first property that we see here. The next one is that multiplication of numbers is commutative, okay, and in this case there's a similar type of property for tensor products, okay, but we're going to call it symmetry. V tensor W is actually isomorphic to W tensor V, okay, so if you use the definition using coordinates, especially in the finite dimensional case, it's quite easy to see. Remember, if this is dimension D and this is dimension E, then of course the dimension of the tensor product is just the product of the dimensions, so it doesn't matter which order you have them, okay, they're going to be isomorphic. But in this case, there's actually a very natural isomorphism between them, okay? So what is the isomorphism between them? If you have an elementary tensor V tensor W, okay, the corresponding element inside here is also an elementary tensor inside here, and I hope you can guess what it is. It's just W tensor V, okay? So that's very nice that you have a nice isomorphism like that. So another property of multiplication is how it behaves with addition. There's a distributive law. So in this case, we see that the tensor product also behaves very nicely with respect to direct sums, okay? So how does that work? Suppose you have W tensor, and over here you have a direct sum V V prime. Well, is it related to the first one, V tensor W, and V prime tensor W? And the answer is this is actually isomorphic to the direct sum of these two tensor products. So this looks just like the distributive law, but instead of an equality here, you have an isomorphism, and it's a natural isomorphism. The third thing that you have here is an associative law. So remember, when you multiply three numbers together, you can bracket them however you feel like. And the same happens with the triple tensor product that you see here. If you do V tensor W first, and then tensor this with X, then this is isomorphic to V tensor W tensor X. And there's a natural isomorphism between them as well. And to tell you what that is, I just need to tell you what happens to these tensors. Okay, these elementary tensors. This is not all elementary tensors in this tensor product, but these will at least span this tensor product, as you can quite easily check. Okay, so where does this go? Well, I hope you can guess. V tensor W tensor X goes to just V tensor W tensor X. Okay, and you can check that this is an isomorphism. So how do you go about proving any such property like this? Well, it's all pretty much the same way, and I'll just do it in the case of the first one here, okay, because it's right interesting, that one there, okay? So as usual, if you want to construct maps out of a tensor product, remember, there's a universal property which allows you to do that. So linear maps out of this correspond to bilinear maps, okay, so as I mentioned. So we're going to construct this bilinear map, which I just mentioned before. So F cross V to V, what you can do is alpha comma V, you're going to map it to alpha V, okay? So this is linear in alpha, okay, and it's also linear in V, so it's bilinear. And once you have a bilinear map, that induces a linear map out of the tensor product. So F tensor V maps to V, okay? And which linear map from here to here is it, okay? So what's the relationship between these two? It's the one that sends this elementary tensor alpha tensor V to the one that's given here. So it's not V here. Let me just correct that. So that's actually alpha V. So this is actually alpha. I'll write it properly. Alpha times V. Okay? So it's whatever this goes to, okay? So that gives you a linear map from here to here. And the only thing that you have to check now is that this linear map is actually an isomorphism. So here I'll just indicate briefly why this is true by giving you the inverse isomorphism. So an element inside here that's such some V, what is the corresponding tensor inside here? It's just one tensor V. Of course, one tensor V, when you multiply the 1 and the V, you get back to V. So of course, that's a natural choice to pick, okay? So that turns out to be the inverse isomorphism. So you can check quite easily that this is a well-defined linear map. And then of course, essentially what I said, it shows you that this is an isomorphism. And that gives you these product type properties, okay? So before moving on, I want to give a little corollary, particularly of this fourth property here, which is the associative law, okay? So what does this tell you? This means that now instead of just looking at tensor products of two things, you can look at triple tensor products, quadruple tensor products, and so forth, okay? So any finite number of vector spaces, you can tensor them together, and it doesn't matter how you bracket them, they will be isomorphic. In fact, you can also swap them around, although we won't use this latter fact, okay? So you have this associative law, okay? And what does that do for you, okay? What do these extended multi-triple tensor products do for you? Well, that's given by this corollary. So remember, one of the reasons for introducing tensor products of two things is it can tell you about bilinear maps, okay? That's the universal property. So let's see what happens when you, instead of looking at two vector spaces, you now have n vector spaces, v1 up to vn, okay? So what I want to do is I want to look at firstly the product of these and the tensor product of those vector spaces. Now, as before, one of the things you can do is you can map an n-tuple of these vectors, okay? So v1 is inside big v1 and so forth. So this is an n-tuple inside this product of these n vector spaces, okay? And you can map it to the corresponding elementary tensor, okay? So there's a map, and that's well defined. There's no problems with that. And what's interesting about it? So why are we looking at it? Well, this turns out to be multilinear in each of its variables, okay? So in other words, if you fix all the variables except for, say, vi, for any of them, so you pick one particular corner, so you think of it now as just a function in that vi, holding all the others constant, then it's linear in that vi. And this is so for any vi. So this is, so if you vary v1 and hold v2 to vn constant, and similarly if you vary v2 and so forth. Okay, so that's great. So you have a multilinear map. And in fact, more is true. So the universal property, which relates bilinear maps from product of vector spaces to some other vector space. Remember there in 1-1 correspondence to linear maps from a tensor product of two things. Now you can extend that, okay? You can look at linear maps out of an n-fold tensor product, so v1 tensor up to vn to w, and what do they correspond to now? They correspond now to multilinear maps from v1 across all the way to vn to w, okay? So this, in the case where n equals 2, is the universal property that we saw before. And now what's really nice is it generalizes to multilinear maps where you have now not just two vector spaces, but n vector spaces. And the proof of this, you can either prove this directly, it's not so difficult, or you just use induction and this fact here, okay? So you know it's true in the case n equals 2. And now this reduces triple tensor products to doing tensor product of two vector spaces twice, okay? So if you do that and you work out what it means, the universal property, and you use induction, then you can also get this result, okay? So I'll let you think about how that works. And that gives us the product type properties. So there's a very, very important, another type of property which involves functoriality, okay? So we've talked about tensor products of vector spaces. Well, something else that you can do is you can take not just tensor products of vector spaces, but also tensor products of linear maps. So let me show you how that works, okay? So suppose now that you have two linear maps, phi from v to w, and phi prime from v prime to w prime, Okay, so what we're going to do is we're going to form two tensor products. Okay, the domains we're going to tensor together. Okay, so V tensor V prime, and the codomains we're going to tensor together. W and W prime, we'll tensor them together. Okay, so the phi goes from this V to this W, phi prime from this V prime to this W prime, and I claim now you can do a phi tensor phi prime, which goes from V tensor V prime to W tensor W prime like that. Okay, so how is that defined? So as usual, to get a linear map out of this, I just need a bilinear map from V cross V prime to here, and so basically I'm just going to tell you where V tensor V prime is. Okay, and where does that go? So I have to give you an element of W tensor W prime. Okay, so the element of W that I'll give you is just phi of this V. And then what's the element of W prime? Well, I have a V prime, so I just apply phi prime of that. Okay, so that's what I have. And now it's very easy to check that as a function of V and V prime, it's linear in V and linear in V prime. Okay, so that tells you that that is indeed a linear map from here to here. That's the universal property. Okay, so that's great. Not only can you tensor vector spaces together, but you can actually tensor linear maps together as well. Okay, so I want to give you just some basic formulae. Hopefully they're easy to remember. Okay, they look a little bit bizarre the first time you see them. Okay, and there's a bit to remember, but if you remember that this is meant to be like a product, then it's actually quite easy to remember the formulae. Okay, so suppose now instead of just one map from V to W, you have two maps, phi 1 and phi 2. So you can add them together before tensoring them with phi prime. Okay, of course you can also tensor phi 1 with phi prime, and phi 2 with phi prime to give you another map, and they both go from the same place to the same place, so from here to here. Okay, and you can ask, well, what's the relationship between this map here, okay, this tensor product, with these two tensor products of linear maps? And in fact, this is just the sum of these two. So this just looks like a distributive law type of result. Of course, you can do the sum on the other tensor factor instead, and you get a similar type of formula. Okay, the other thing that you can do is, well, let's suppose that now instead of having a map like this from V to W, you have one map like this. You have also something that you can compose. So you can do phi 1, phi 2, tensor phi 1 prime, phi 2 prime, okay? Well, then also you can do a phi 1 tensor phi 1 prime and a phi 2 tensor phi 2 prime, and you can compose them and ask whether they're the same. And the answer is that these two linear maps are the same. Okay, so if you're a bit lost as to where these goes, let me give you the proof of this one here. So the proofs of these two, in fact, they're fairly straightforward. You just sort of wind through the definitions. So I'll just wind through the definitions and show you how that works. And I'll show you how that works by looking at the right-hand side, okay? So suppose you have this, well, the first map you have here is phi 2 tensor phi 2 prime. Okay, so suppose phi 2 goes from V2 to V1, and phi 2 prime goes from V2 prime to V1 prime. So phi 2 tensor phi 2 prime goes from this tensor product to this tensor product here. And all it does, so remember how this works, how does a tensor product of linear maps work here? If you have an elementary tensor, V2 tensor V2 prime, you just apply the phi 2 to the first one, phi 2 V2, and a phi 2 prime, the second tensor factor here to the second tensor factor here, phi 2 prime V2 prime. Okay, so that's the first map. And suppose now you have a phi 1 which maps this V1 to V0, and this phi 1 prime which maps this V1 prime to this V0 prime here. Okay, now what does this second map do? Well, phi 1, this tensor product, what does it do to the first tensor factor? So this is still an elementary tensor here, so you just apply phi 1 to this first tensor component, so you get phi 1 phi 2 of V2, phi 1 phi 2 V2, and you apply this phi 1 prime to the second tensor, so phi 1 prime phi 2 prime of V2 prime. Okay, so the composite starts from this V2 tensor V2 prime, and it ends up at this elementary tensor over here. Okay, so that's the right-hand side. That's what happens there. But what does the left-hand side do to this one? Okay, so this is one tensor product, so you just have to apply this phi 1 phi 2 to this V2 as the first tensor component, so you get phi 1 phi 2 of V2. Okay, that's the same as what you have for the right-hand side, which is good. Okay, and then you apply the second one, phi 1 prime phi 2 prime, to the second tensor factor. Okay, so that's phi 1 prime phi 2 prime, phi 1 prime phi 2 prime of this V2 prime. Okay, and hope that unravels a little bit what this formula is trying to say, and also shows you that actually the proofs of these properties are fairly straightforward, okay, but they're extremely useful. A very important application of tensor products of vector spaces is the notion of complexification. And to motivate this, I want to pose the following question. Okay? Suppose you have a real vector space. Is there a natural way to associate to that real vector space a complex vector space? Well, in a more complicated sort of setting, we can also look at linear maps of vector spaces over the reals. So if you're giving a real linear map, can we associate to that a map between complex vector spaces? So that's the question I want to pose, and I want to do this in a slightly more general setup, where we don't just have an extension field C of R, but a more general extension field F prime of F. And the construction that I want to give is the following one here. Okay, so suppose we start off with just some vector space V over the smaller field F. Okay, I need some additional notation here. So given alpha, an element of the extension field F prime, I want to look at multiplication by alpha. Okay, so I can make this a map from F prime to F prime. Okay, just multiplies by alpha, so gamma goes to alpha gamma. Okay, so that's just some notation. Okay, so what can we do? I want from this F space V to generate a vector space over F prime. So the first thing I can do is I can form this vector space tensor product, F prime tensor FV, which is a vector space over F at least. But I want to actually extend that action to action of F prime. So it's not just an F space, it's an F prime space, okay? And how do I do that, okay? So of course this is a vector space over F, so it has an addition, and I just need to tell you how to scalar multiply by elements alpha inside F prime, okay? So what is scalar multiplication by this alpha? So let me tell you what it is. Well, remember, you have this tensor product of linear maps. I can do M alpha on this F prime, that's this M alpha on this F prime, and I can do the identity on this V. So I can take the tensor product of these to get a map from F prime tensor V to F prime tensor V, and it turns out that that will make this not just a vector space over F, but in fact a vector space over F prime, and in fact, moreover, this F prime vector space structure extends the F vector space structure on this tensor product. Okay, so that's really nice. Okay, and it's quite simple, and it just follows from our construction of tensor products. Okay, I won't go through the proof of that. So now suppose you have a linear map, an F linear map between vector spaces over F from V to W, that's phi. Now you can apply this construction to get you F prime vector spaces, okay? So F prime tensor FV and F prime tensor FW. And the point is now, this F, which is a linear map from this V to W, will induce a F prime linear map from F prime tensor FV to F prime tensor FW. Okay, and how does that work? Okay, so we're going to define it in a similar way. It's just going to be a tensor product of linear maps. So what does it do from F prime to F prime? It's just the identity. It doesn't do anything. It leaves that. And how does it go from V to W? Of course, I hope you can guess it, just as phi. So it's just the identity tensor phi. Okay, so we saw that that's an F linear map, but you can check quite easily just using the definition of the scalar multiplication given here that in fact it is F prime linear. Okay, so that's the way we have from an F space, we can induce an F prime space using the tensor product, and given an F linear map, you can get an F prime linear map on the corresponding F prime vector spaces. Okay, so it looks a little bit abstract at the moment, so let me give you a very, very simple example where F is just the reals and F prime is the complex numbers, and let's pick the simplest possible vector space V here, which should just be Rn. Okay, so what's C tensor Rn? Okay, what is this complex vector space? Okay, so I want to use all the properties that I gave you. Okay, so the first thing is that this Rn you can write as a direct sum of R times these EIs. Okay, where EIs is the standard basis vector. So this is I equals 1 to n. That's the range. Okay, so you have a tensor product of this C with this direct sum, and remember we have the distributive law. So now we can rewrite this using the distributive law. You can pull out this direct sum. It's just a tensor. Direct sum of these tensor products C tensor R REI. Okay, so that's what you have here. And now what is this? So remember, this is essentially just isomorphic to R, and the isomorphism is given by the basis vector here. So this is just C tensor R over R. You can use the unit property here. This is just a copy of C. It's a copy of C, and to say which copy of C is, well, what's the corresponding basis vector of that? Well, if you trace out how the isomorphism works, it's just 1 tensor EI. Okay, so this is just a direct sum of copies of C, okay, where the copies of C, they're given by this basis one tensor EI, where the I ranges from 1 to n, so that's just C to the n. So that's rather nice. How have we converted this real vector space Rn to a complex vector space? We just basically replace this with Cn, okay? Although it goes through this isomorphism here. Okay, so this is actually not a complete proof, because when I gave you these properties, the distributive law and the unit law, they are only isomorphisms of vector spaces over R. But you can check using the definitions here that this is actually isomorphisms of vector spaces over C. Okay, so this actually gives you an isomorphism of vector spaces over C. So that's very nice. Okay, it's a very, very simple sort of a construction here. Okay, so you can really see what's going on. Okay, so let's now look at the simplest example of what a linear map is. So what's the simplest example of a linear map? That's given by a matrix. So suppose you have a real matrix, okay, and it's going to give you a linear map phi from Rn to Rm. Okay, then what does C tensor R phi do? Okay, so what does it do? So basically what you do is you just let phi act on the second tensor factor. Can you leave the f prime bit the same? Okay, so you're letting phi just acting on these EIs. Okay, now if you think about what happens here, remember, to work out the representing matrix, you just have to say how does it act on the standard basis vectors, and how do you rewrite that out as a linear combination of those standard basis vectors. So in this case, what does this do? This phi just acts on these standard basis vectors. Okay, and it just acts in the same way on these standard basis vectors. Okay, but now you just write it instead of an EI as one tensor EI. That's all I've done. So really the representing matrix of this C tensor R phi is the same. Okay, it's the same matrix as the one you had for this map phi from Rn to Rn. So the only difference is basically if you have a linear map from now, this will be a linear map from Cn to Cm, okay, that is really should be a complex matrix. So the point is that the representing matrix of this linear map here is actually the same matrix, okay? It's the same matrix, but you're thinking of it as a complex matrix as opposed to a real matrix, okay? So really it's a very subtle little point here, okay? It's the same matrix, but you want to think of it as a real matrix instead, as a complex matrix instead of a real matrix. And actually, you should have seen in your linear algebra that this is the type of thing that you do quite a bit, okay? So when is that? So suppose you want to look at a real matrix and you want to study it, a real square matrix, then what do you want to do? Often you want to apply eigenvalue, eigenvector theory. But when's the best time to study that? Okay, it's difficult over R because you don't have all the roots of the characteristic equation. So what do you do? Well, the roots of the characteristic polynomial. So what do? You work over the complex numbers instead. So you look at that real matrix, real square matrix, and you pretend it's a complex matrix, okay? So once you do that, you can diagonalize over the complex numbers, okay? So what we've done here basically is we've taken that idea, this simple idea of taking a real matrix and thinking of it as a complex matrix. Okay, so that's a procedure that you can do on matrices. And as with most nice procedures that you can perform on matrices, you should be able to generalize that to the setting of linear maps. And that's what we've done here, okay? This simple procedure, which in terms of matrices is so banal, just thinking of a real matrix and just thinking of it as complex matrix, okay? What's the linear analog, the linear generalization of that? So if you have a real linear map corresponding to that matrix, how do you get the corresponding linear map on complex vector spaces? Well, now we've actually got the procedure for doing it, okay? So if you're given a linear map phi, now from between any two vector spaces, you have the corresponding complex linear map, which is just C tensor R of that phi, okay? And a typical use for that, as I mentioned here, is often when you extend scalars in this way, so this is a general notion called extending scalars. If you extend scalars from R to C, then often your life becomes simpler. I hope you enjoyed this adventure in pure mathematics.